We've looked at how to use Pythagoras and trig ratios to work out lengths and angles in cuboids. We can use the same techniques to find out lengths and angles in more complex shapes such as pyramids. We just have to take more care about drawing these diagrams and recognizing exactly which triangles we're going to be dealing with as we use Pythagoras and trigonometrical ratios. We're going to look in this video at a square-based pyramid with equilateral triangles on each side. This makes it slightly simpler, but the methods are the same whatever the shape of the pyramid and whatever the shape of the triangles up the sides. So let's draw what this pyramid looks like. It's got a square base and it's got triangles making up the face on each side. The base has edges of 10 centimeters in this case. And because the base has edges of 10 centimeters and we have equilateral triangles, the lengths of the sides CE, DE and so on are all 10 centimeters. The question we're being asked is calculate the height of the pyramid. First of all, we're going to mark a point on the base of the pyramid that's directly below the apex E. And so the distance E to F is going to be the height of the pyramid. Now we know that ABCD is a square. So if we draw a triangle there, the triangle ADC is right angled. And we know that the sides of that triangle are 10 centimeters. And we can use Pythagoras to work out the distance from A to C. So AC is the square root of 10 squared plus 10 squared, and that's the square root of 200. And the distance from A to F, the centre, is going to be half of that distance, and half of the square root of 200 is the square root of 50. We've now got a little bit more information than we started with. We know the distance from one corner to the centre of the base of the pyramid, and that's root 50. It's about 7.1 or so. So now we're going to consider the triangle that goes from A to F and then to E. Let's draw that, but put it down separately on our page so we can see exactly what it's like. There's AFE. We know the distance from A to F is root 50. We've just worked that out. We also know the distance from A to E, because it's one of our equilateral triangles, is 10. So we can now use Pythagoras to work out the height from E to F. Because we know the hypotenuse on one other side, the Pythagoras equation is going to be a subtraction one. So EF is equal to the square root of 10 squared minus root 50 squared, and that is the square root of 50. And as we mentioned before, that's 7.07 or 7.1 if you do it to one decimal place. So with two fairly quick steps there, we've worked out the height of that pyramid by recognizing the triangles that exist within that pyramid and using them to our benefit. In this case, to work out the lengths, we've only needed to use Pythagoras. Let's quickly ask ourselves, does the answer make sense? Well, if the distance from D to E and from C to D up those straight lines along the edges of the pyramid is 10 centimeters and they're sloped, well, the distance from the top to the bottom is going to be less than 10 centimeters, but given the slope, it's not going to be a great deal less, so 7 is going to be in the right ballpark for our answer. If we'd have got an answer of more than 10 or less than 5 perhaps, we'd have wondered whether we'd done something wrong with our calculations. Having used Pythagoras to work out the length, we can now look and try and work out some of the angles in this pyramid. So let's work out the angle between the triangular faces of the pyramid and the base. And to do this, we're first going to look at what is the midpoint of that line AD. Let's mark that on our diagram, and then we can draw the triangle MFE. Now that looks a bit of a funny shape in there because our drawing is not fantastic, so let's move that down the page so we can see what it looks like. It is a right angle triangle, obviously, because the distance from F to E is a perpendicular height on the base, and we know what that height is. It's 7.07. We also know that the distance from M to F is going to be 5 because it's halfway from one edge to the centre, and one whole edge is 10 centimeters, so half of that is 5 centimeters. So now we have a triangle where we know two sides. We're looking to find out the value of x degrees there. This looks like a good time to pull out those triangles we've been using before. Here they are. We know the opposite and the adjacent. Which one has O and A in it? Well, it's the one at the end there with TOA, isn't it? So we can get rid of the other two and just use our tangent equation. So we know that tangent of x degrees is the opposite divided by the adjacent. So that's 7.07 divided by 5. So the tangent is 1.414. If we get our calculator out, do tan to the minus 1 of 1.414, we get a value for that angle of 54.73 degrees. As usual, we're going to ask the question, does the answer make sense? Well, the height is longer than the distance across, the 5 centimeters, so clearly the value of the angle is greater than 45 degrees. It's not going to be a great deal greater than 45 degrees, so we're probably in the right area. So we haven't done anything really foolish in getting that answer. As with all other trigonometrical and Pythagoras questions, the key to getting these right is drawing a suitable diagram, making sure you've selected your triangles carefully, making sure you've labelled them with the right values, and if you do that, it's less likely that you're going to make some silly mistakes.